Okay, welcome back. We are looking today, continuing Unit 2, our equilibrium. We're looking at something we call enthalpy. We've seen that before, the heat of reaction on our potential energy curves, and entropy. So, start off with enthalpy. We've seen enthalpy before. It's the change in potential energy. It's kind of the heat content, the energy contained within our system at any given time. So we're going to look here at exothermic and endothermic reactions. So just a reminder, our change in enthalpy, delta H, here we have a decrease, it's negative. And here we have, for our endothermic reaction, an increase in enthalpy. So our change in enthalpy is positive delta H. So the enthalpy is the heat content. It's really the energy, the potential energy at any given time. So looking at these curves, potential energy is really the enthalpy. Think about that. And what the rule we're going to follow here is systems will tend toward a state of lower potential energy as long as there's nothing acting upon it. So what that really says is nature is going to favor a more stable state. Okay, so the more stable, lower energy arrangement is going to be favored. So in an exothermic reaction, our products are favored. So nature tends to want to exist down here as the products. That's why many of these exothermic reactions are spontaneous, right? We have spontaneous combustion, and then things tend to stay this way as in the product form. An endothermic reaction, our reactants have lower enthalpy, and our reactants are favored in an endothermic reaction, or at least our enthalpy favors the reactants, okay? So we want to favor minimum or lower enthalpy. Okay, that's what we want to look at for enthalpy. So a little bit of practice here. Can we identify endo and exothermic and identify what has minimum enthalpy? So what I would suggest, if you need it, is think about the visual of our endothermic curves and our exothermic potential energy curves. Enthalpy being the potential energy. So for endothermic, our reactants are lower. For exothermic, our products are lower. So question 1a, we've got this reaction. Delta H is given to us. Delta H, notice it's positive. And since it's positive, I know that I'm endothermic. I'm going uphill there on my potential energy curves. And then my reactants have lower or minimum enthalpy. They're lower on that energy curve. Question B, we've got our energy term on the reactant side. That's energy being added. So remember that's identifying this as exothermic, or pardon me, totally backwards, endothermic. Okay, since we're endothermic, again, my reactants have lower or minimum enthalpy. And question C, my change in enthalpy delta H is negative. So that would be a decrease in enthalpy, going down by the 25 in this case. So that's exothermic this time. Exothermic, my products are lower. My products have lower enthalpy, or minimum enthalpy. Question 2, if enthalpy is considered, are the reactants or products favored? So we're going to, what the statement on the last slide said was we're going to favor the lowest enthalpy. So similar to question 1, first we have to decide, are we endo or exothermic? So this heat term being on the left-hand side tells me that I must be endothermic. So I'm increasing by that 92.4 kilojoules. So that being endothermic means my reactants are lower. We're going to favor the reactants. Enthalpy will favor the reactants, we should say. Question 3. We've got a negative delta H. Negative delta H means we're going decreasing by that 25 kilojoules from reactants to products. So my products are lower in enthalpy, and therefore my products are favored by enthalpy. But there's an issue with this. If we look at this equilibrium between our solid water, ice, and liquid water, we've really got an equilibrium here, right? If we had ice cubes in a glass of water at 0 degrees Celsius, we'd have an equilibrium system where we've got that phase change of melting and solidification happening at the exact same rate, the exact same time. If we look at enthalpy here, well, we know that it takes heat, takes energy to melt this, right? It takes some energy. So that's an endothermic process. And endothermic reactions, we have lower enthalpy on our reactant side, which is our solid water, or ice in this case. That would mean that we should favor that left-hand side. So enthalpy, if it was only up to enthalpy, then enthalpy would want all of the water to exist in the solid form, because that's the lower energy state. We know that's not true. We know that not all water on Earth favors that solid form. We know that we often have the other phases, so there's got to be some sort of, there's something else going on here, essentially. And that something else is something we call entropy. And entropy is a term given to randomness or disorder in a system. So entropy refers to disorder or a lack of order. Randomness is often what we say. Okay, so when we look at systems that are sort of more highly ordered and arranged in terms of the atoms in that system, then we have low entropy because we don't have very much randomness. Okay, so less randomness, lower randomness means lower entropy, less entropy. And then if we look at a phase like gas, for example, over here, the more random those particles could be arranged. So at any given time, if you were to take a snapshot of that system, the arrangement of all these particles, I mean, it'd be different every time. There's so much randomness in terms of how they're arranged relative to each other. And the higher that randomness, the higher what we call the entropy. Okay. Now, the rule with entropy is that nature always tends to move towards a more disordered state. Okay, so the analogy here, your room doesn't clean itself, right? If you let time tick on, well, you know, my classroom, your bedroom, whatever, it tends towards a system of more disorder. You know, things get more cluttered, more disordered, more random in terms of where things are. They don't tend to just naturally on their own stay in a nice ordered state. We can make them be that way, but we have to put energy in to kind of reverse that process of becoming disordered. Okay, so your room doesn't clean itself. Things tend to become more disordered. Another analogy here, if we let a beaker fall off the table, it tends to obviously break into a whole bunch of pieces. Okay, nature tends to exist that way and remain in this highly disordered state. Is nature going to randomly on its own order itself and somehow have the random arrangement of pieces of glass all of a sudden arrange themselves spontaneously into an ordered shape of a beaker? It's just not going to happen. Okay. So here's the kind of indicators in terms of when we're trying to look at entropy, we look at the phases. Okay. So lower entropy, less entropy. Now we give entropy the symbol S, okay? So lower entropy in our solids, a little bit more in our liquids, more when we have aqueous solutions, even more when we have gases, and then even more when you have got more gases. So the highest entropy being when you've got the most amount of gases present in your system. So that's what we're going to look at, is just the phases. So here are some examples, and notice I'm just going to look at the phases in my system here. So all of these have the double arrow. These are all systems at equilibrium. So we've got reactants and products both present. We have them, they're already there. That reaction is happening already in the forward and reverse direction. So all we're trying to decide here is, do my reactants or products have the most entropy? So solids have less than liquids, which have less than aqueous, which have less than gas species. So question A, my reactants, I've got something in the solid phase. My products, I've got something in the aqueous phase. My aqueous phase is going to have certainly a more random order arrangement of kind of where those atoms are at any given time. So my products have what we call the most entropy in that system. Question B can be a little bit tricky. If I look on my reactant side, I've got some gas. On my product side, I've got some gas and some more gas. So we got to be a little bit careful here. So what I'm going to look at on the reactant side is I've got 2 moles of gases. I've got 2 moles of gas on the reactant side. On the product side, I've got 1 mole of this nitrogen gas and 3 moles of hydrogen gas. So I actually have 4 moles of gas. So here I'm going to compare the amount of gas. So that's why on the last slide we said that we can then talk about more moles or more gas. The more gas you have, the more random arrangement of all those gas particles can be. So in this case, my products again have higher or greater or more entropy. Question C, I've got a mole of this ammonia gas. On the product side of that same species but aqueous. So in this case, my reactants have higher entropy. And question D, we've got, again, just look at your phases. So I've got gases, gases, gases. So that means now you gotta, if you have gases on both sides, which we do, we gotta count them up. So on the left-hand side, my reactant side, I've got 1 mole and another mole. I got 2 moles of gas. On the right-hand side, the product side, I have 1 mole of gas, which is less. So my reactant side has higher entropy. Question E, look at the reactant and product side. On the reactant side, I've got solid and aqueous species. On the product side, I've got aqueous, liquid, and gas. Don't worry about having to compare all these different kind of phases. All we care about is where do we have the most entropy. And as soon as you see gases, then you know, and you don't have any gases on the reactant, the left-hand side, then we know that our products are going to have the highest entropy. So really look for gases. Look for gases first. If you have them on both sides, count them up to compare each side. And then you can look on down the line as to whether you have solids, liquids, aqueous, that sort of thing. So now what we have to do is put both of those rules together. Nature tends to move towards a state of lower enthalpy, so it's a lower energy state, but a higher entropy state. So lower energy, higher disorder, higher entropy. So we've got kind of 3 possibilities here. The first is, no particular order, the first is enthalpy and entropy both favor the product side. Okay, so let's look at an example of that. So here we have this example of zinc metal in our solution of hydrochloric acid. Looking here, we know this is exothermic. It's got a negative delta H. Okay, so let's look at, doesn't matter which one you look at first, let's look at entropy. If I compare entropy, then we're just going to look at our phases. That was like the last slide. So solid, aqueous. On the right-hand side, we got gas, aqueous. Okay, so my right-hand side, the most entropy, highest entropy, favors the products. Check enthalpy. To compare enthalpy, you think about endo or exothermic, and which side's lower is where it wants to be. So we know this is exothermic, so that's going to be lower energy, lower enthalpy on the product side. So it favors the products. So now you look at which side each one favored. These are both favoring the product. So really you've got 2 votes. Both of these votes want this reaction to proceed towards the product side, the right-hand side, which means that this reaction goes to completion. So when you have both of them favor the right-hand side, enthalpy and entropy, S, then we're going to have a reaction that goes to the right-hand side, which is to our product side, and this reaction goes to completion. Neither one of these want that reaction to move towards the left in the reverse direction. Second possibility, if your enthalpy and your entropy favor the reactant side, the left-hand side, then we're going to say that this reaction doesn't occur at all. So here's an example. Notice my heat term is on the left-hand side. So you should be able to think about, is that exothermic or endothermic? So first let's check entropy. The entropy here I've got on the left-hand side, I check phases. So solid, got 3 moles of gas. On the right-hand side, I've got gas. So I got gas on both sides, right? So that's where I got to compare the amounts. So I got the 3 moles of the gas and 1 mole of gas. So my entropy is highest on the reactant side. Okay, so entropy wants that reaction to be pushed towards the left, the reactant side. Check enthalpy. Well, looking at the heat term on the left-hand side, we should be able to figure out that this is endothermic because heat's being added here. Endothermic favors the enthalpy favors the left-hand side, lower enthalpy on the reactant side. So we have enthalpy H also wanting that reaction to be pushed or moved towards the left, the reactant side. So now we got 2 votes. Each vote wants this reaction, this system to be reactants. They don't want this system to be products. They want this system to lie towards the left-hand side, and that's what will happen. Okay, we're going to predict that this reaction does not occur. These reactions are not going to turn into products because these 2 factors don't want them to. Now, the third possibility is we have enthalpy and entropy favor opposite sides. One wants to move to the right, one wants to move to the left. They both get a vote, so both of those happen. So this one here, let's check entropy. So I notice I've got 1 mole of a gas. I got more gases, so I got to count the moles. So 2 moles of gas on the right-hand side. So entropy S, if it was only up to entropy, it would want this reaction to move towards the product side. That's what it would want to occur. Check enthalpy. Now notice this is a positive delta H. Positive delta H means endothermic. So enthalpy favors the reactant side. So we have enthalpy wants that reaction to be pushed towards the left. So we have entropy, S, which would like this system to only exist as products. We have enthalpy, H, which would like this system to exist only as reactants. Now, neither one wins. They both essentially kind of win out. And what happens here is when they favor opposite sides, then that forward reaction, so I'll just highlight this forward reaction happens, and so does this reverse reaction. Both of those reactions happen in forward and reverse, and that's our equilibrium. So this system will reach equilibrium, where they're both occurring due to the opposite votes from the entropy and enthalpy. So a little bit of practice here. Let's figure out which side is favored, okay, for each of these. So I'll run through these kind of in the way that I would, and you can write down, as much as you need to. So I'm going to check enthalpy first. Delta H is negative, okay? Negative meaning, I'll just write this over here. Okay, endothermic is positive delta H. Exothermic is my negative delta H. Okay, endothermic favors reactants are lower. Exothermic, my products are favored, they're lower. So this is negative over here, delta H. So that is exothermic. So looking at my diagram over here, enthalpy favors the product side. That's where energy is lower. Now I got to check entropy. Check your phases. So here I have gas, gas, on the product side, gas. So that means I got to count them. On the reactant side, I've got 2 moles of gases. On the product side, I've only got 1. So I have more gases, so therefore more entropy on the left. So these two factors oppose each other. So the forward and reverse reactions are going to happen. This reaction we would predict to reach equilibrium. Oh boy. Okay. Question B. Again, check your enthalpy and check your entropy. So enthalpy, we look at endo, exo, which side's lower in energy. So this has energy on the right-hand side. That's energy being released. So that's exothermic, which means my products have lower energy. Enthalpy favors the products. Entropy, check the phases. So here I have 2 moles of gas. On the right, I have 1 mole of gas. So that favors the reactants. Again, those two things oppose each other. So I would predict this system to reach equilibrium. Question C. Check your enthalpy and your entropy. So this one has heat on the left-hand side, my reactant side. That means that heat must be added to that system to give a positive delta H. So that means my reactants are lower in energy. Entropy, S, check your phases. So look for gases. So it's solid. So here I got 6 moles of gas. Over here I got 4 moles of gas on the right-hand side. So gases and gases, so check the amounts. I have more gases on the left, more disorder on the left. Entropy will be higher on the left. So both of these favor the left-hand side. So I would predict this reaction to not occur because neither one of these factors would like that reaction to proceed to the product side. And the last one, we've got a negative delta H. Negative means I'm exothermic, so my energy is lower on the right-hand side. And then for entropy, check the phases. So first look for gases. So I've got, on the reactant side, I got some gases, more gas. On the product side, I have no gases. So I don't need to bother counting. Because I have gases on the left and none on the right, I know that entropy is higher on the left. So these oppose each other, so I would predict these to reach equilibrium. Okay, I'm going to stop there, and you will try some of these out in your assignment.